Hello? Okay, so let me just check if the sound is working. Let's see. It's actually very interesting. I've been talking to AI about Gödel's incompleteness theorem, and the conversation is interesting, and I want to do an experiment to see if AI will answer differently. So let me see if the sound works. So let me see. Do an experiment. Okay, the sound works pretty good. Okay. Um, so let's switch the scene. Let's see. I need to. Okay, so how do I capture my screen? Okay, there we go. Okay, so this is the conversation. So what I'm trying to understand is, so Gödel's incompleteness theorem proves that there are statements that are true, but we cannot prove them within this system. Okay, I do not mind that. And that is, I think, true because he proved it. And the proof is right here. We can look at it. Um, let's go down. Here they mentioned it. The AI mentioned it multiple times. Um, okay, so for example here, uh, the Gödel's sentence, this statement is not provable in system PA. It is true if PA is consistent. It cannot be proven in PA. Why this works? We do not prove the statement's truth within PA. We accept it as true because PA is consistent, which is a meta-mathematical assumption, not a formal proof. No, this isn't what I'm looking for. Okay, so anyway, so the, the proof is like this statement is not provable in PA. Um, hold on. Okay, this is my first live stream. Okay, let's see, first live stream on YouTube. Let's see, proof of Gödel's. Let me just ask it. Proof of Gödel's incompleteness theorem. First, theorem. Okay. Gödel's first incompleteness theorem demonstrates that in any consistent formal system capable of basic arithmetic, there exist true mathematical statements that cannot be proven within that system. Here's a simplified intuitive proof outline. Mm, okay. Okay, so assign a unique number, a Gödel's number, to every symbol, formula, and proof in the system. Okay, so we assign a number to every formula prove combination of anything within a system. So for example, the plus sign, you give it the value 1. Uh, 0, we give it the value 2. I think that symbol is for all, we give it value 3. And a formula like the Pythagorean formula, we give it value 200. Doesn't matter. We give a value to every combination within uh, within for every combination that a system uses to make any statement, as far as I understand, is what that means. This allows the system to encode and reason about its own statements and proofs as arithmetic propositions. Okay, so rather than using symbols and formulas, we're just gonna use numbers. Okay. Construct a probability predicate. Define a formula probability n in the system that means the formula with Gödel number n is provable. Okay. Probability n is expressible because the system can encode its own proof-checking algorithm. Probability n is expressible because the system can encode its own proof-checking algorithm. Okay. Okay, so the system can check its own proof. For any formula phi of x, there exists a sentence G such that G G to phi of x of, I guess, what is that? Is that like G bar? What does that mean? Is phi of x to phi of x G bar to G. So here G bar is the Gödel number of G. Okay, okay. So G bar is so G brackets is the Gödel number of G, and phi is a property we define. This lemma allows statements to refer to their own Gödel numbers. Okay, okay. So we make a function that refers to any sentence in the system to the number. Okay, okay. So construct the Gödel sentence G. Apply the diagonal lemma to the formula. I guess that is bar probability of x. I'm not sure what that's. I'm not sure what this means here. But yeah, I guess it's bar. This gives a sentence G such that G to bar probability um, Gödel number G. In plain language, G is true if and only if G is not provable in the system. Okay, so this is perfect. So the statement G is true if and only if G is not provable in the system means that that statement refers only to statements in the system that are true but that we cannot prove. Okay, perfect. Assume the system is consistent. I'm not sure if you have to assume, it doesn't really matter. We're talking about the system. Oh, okay, there are no contradictions in the system. Otherwise, if there are contradictions, let's take the contradictions out. Case 1. If G is provable, then probability Gödel number G holds. Okay, of course, because it holds because well, the thing is, if G is provable, then it's not even contained in this statement right here. So it doesn't really matter. Case 1 doesn't really matter because it's not the case that we're looking for, but it's there. But G to bar probability G, Gödel number G, so G would be false. Uh, yeah, because it's not because if it's provable, then G isn't true because it's only true if it's not provable. Okay, so case 1, yeah, okay. This contradicts consistency. The system proves a false statement. So case one is to get rid of the unnecessary clutter, you know. Anyways, case one is important to look at. The real butter here is in case two. Case two, if G is not provable, then bar probability, the Gödel number G holds. By definition of G, this means G is true. Okay, so if statement G is not provable, then that statement is true because we define G as true if and only if G is not provable in the system. Well, I don't know how you think. Okay, so I guess there is this next step here that I'm going to look at right now. But what I would say here is, um, how do you know G exists at all within the system? But let's continue. If the system is consistent, G is true but improvable. Yeah, but how do you know that G is in the system? G is true but unprovable within the system. Thus, the system is incomplete. Now, I haven't gone into yet the interesting thing about the AI, about the earlier conversation. I'll go into that in a moment. I'm just trying to understand why Gödel's incompleteness theorem is true. Okay. Um, G prime's truth is established outside the system via meta-mathematical reasoning. It is established outside G prime's truth is established outside the system via meta-mathematical reasoning. So it cannot be proven within the system. You prove it outside the system. If the system is consistent, G's improvability implies its truth. If the system is consistent, G prime's unprovability implies its truth. Yes, but how do you know G is in the system? Okay. How do you know G as defined is in the system? Let's see. I'm actually enjoying this. I'm gonna do this every day. What? It says here YouTube is not responding. What? Um, no, I guess I hope I'm still streaming. Let's see if the sound works. I hope the sound works. Do an experiment. Yeah. See if AI will answer different. If it's not okay. So the sound works. Well, I just hope I'm still. Let's see if the sound works. I'm laggy though. I think I'm laggy. Okay, let's continue. To address the question, how do you know G, the Gödel sentence, is in the system? We need to carefully unpack how Gödel constructs G and ensures it is a legitimate formula within the formal system. Here's a step-by-step explanation. So right now, I'm still unpacking Gödel's theorem, okay? First incompleteness theorem. We're gonna get into the second incompleteness theorem as well later, if you have time. Represent logical statements, proofs, and syntax as numbers so the system can reason about itself. Assign a unique number, a Gödel number, to every symbol formula. Okay, so we do that. Representability of recursive functions. Key insight. The system can encode all primitive recursive functions, e.g. addition, multiplication, substitution as formulas. For example, the function substitution, subtraction, and which substitutes the Gödel number m into the formula with Gödel number n, okay, is expressible in the system, okay? Any computable syntactic operation, example, checking if a formula is a proof, yes, can be represented as an arithmetic formula, okay? Constructing the provability predicate. Definition. Probability X is a formula in the system that means the formula with Gödel number X is provable. Probability predicate. Okay, probability predicate. What does predicate mean? What does predicate mean? The part of a sentence or clause containing a verb and stating something about the subject. Okay, so like John went home is a predicate. Okay, so predicate is okay. Probability predicate. So it talks with. So it says basically. So it's basically a verb or something. Let's say an advanced adjective, whatever. That that is about probability, or it just means function probability x whether it is probable, whether x is probable. Definition: probability x is a formula in the system that means the formula with Gödel number x is provable. Okay, the formula with Gödel number x is provable. The formula with Gödel number x is provable. Um, okay, so I don't know, like, does that function like, okay, so here's the thing. It seems to me that the probability predicate, probability x, is a Boolean function, so it's either, the answer that's gonna give is either like 0 or 1 or something like that. It's like one of two things, whether it's provable or unprovable. Okay, but I'm not sure if that is an issue. Okay, define a formula, proof yx, meaning y is the Gödel number of a proof of the formula. Okay, okay, let's see if they can, if he can simplify it. I just want to know. I just need to know. Let's do enough deep thinking to know. I just need to know whether, how we know. I just need to know why G is in the system. It simply could be outside the system. We cannot say, for example, square root, we cannot say, for example, let's assume uh, complex numbers are in R. Okay, I mean, that's basically what I want to know. I just want to know why that thing is there. You're absolutely right to question whether G is truly within the system and not some external question. To be careful to explain why G is probably a formula in the system and not an external assumption. G is constructed using the system's resources. The key point is that G is built entirely from the system's own syntax and rules. Okay, here's how. Every symbol, formula, and proof in the system is assigned a unique number, a Gödel number. Okay? The system can express primitive recursive functions. Okay? The system can talk about its own syntax and proofs using arithmetic formulas. Okay? The probability predicate. Probability X is a formula in this system that means okay, now I understand what that means. Okay. So the probability predicate simply is an assertion. Okay? It's a formula, an assertive formula. The formula with Gödel number x is provable. It's not a Boolean function, it's a formula that asserts that a Gödel number x is provable. It is constructed using the system syntax and presentable functions. For example, probability x uh, for every, I guess that means for every y that exists is in the system. G is built from the system symbols using standard logical rules. Semantics. G prime's meaning, I am not provable, arises from its Gödel number structure, not from external assumptions. Okay, I'm gonna just assume that is true because it's kind of irrelevant to what I'm getting into today. G is not like assuming complex numbers in R. Instead, it is a formula probably existing within the system, constructed within the system or reasons. Verifying G is in the system. Okay, let's verify G is in the system. Check Gödel number. The encoding of formulas as numbers is purely arithmetic and uses only the system's resources. Okay. Check representability. The probability predicate, probability X, is accessible in the system. Okay, so to check whether the G is in the system, you have to see whether probability X is in the system, right? The probability predicate, probability X, is accessible in the system because it relies on recursive functions. Okay, so the function probability X, it checks if a formula is proved that would make it Boolean. But, because if it checks whether a formula is proved, then you have to know like probability X equals true or false. Apply the diagonal lemma. This is a theory of the system ensuring G is a well-formed formula. Apply the diagonal lemma. This is a theorem of the system ensuring G is a well-formed formula. This makes me feel like I need to watch a video on Gödel's incompleteness. And let's ask actually ChatGPT and Claude first. Then I may be able to explain this better. Prove to me in simple terms why Gödel. Oops, I'm gonna get back to that later. Leak. Why Gödel's first incompleteness theorem is true. Okay, intuitive way. Well, the thing about Claude, by the way, I love Claude because Claude has personality. Unlike ChatGPT, unfortunately, ChatGPT is like kind of dry. Claude has like its own Claudish personality, which makes it very kind of attractive as an AI. It feels more anthropic, right? Anyway, let me break down Gödel's first incompleteness theorem in an intuitive way. The key is to understand how he created a mathematical statement that essentially says this statement cannot be proven. But that statement is a true statement. Okay. Oh, wait. Okay, let's go through this. Let's think about it. Let's walk through it step by step. First, imagine we have a formal mathematical system like arithmetic that can express basic mathematical statements. Gödel found a clever way to encode mathematical statements as numbers. Okay, this means any statement about mathematics could be represented as a number. By the way, uh, this also in a way relates to physical phenomenon because in a way all physical phenomenon can also be represented as a number as a consequence of this. So in a way, all matter is a field of numbers. But anyways, we can come back to that at a later time. Conceptually, though, I think. I mean, something to think about. Actually, maybe no. Um, well, the thing is, the relationship between numbers may be too complex to express in just natural numbers, simply because natural numbers may not have reach. But um, well, maybe if we keep including like larger number classes, like complex numbers, uh, quaternions, etc., then you may be able to. Then that is how you accommodate everything into numbers eventually. So I think that maybe. I'm not sure. I'm gonna look into that. I have to look into that later at some time. Including this means any statement about mathematics could be represented as a number, including statements about other mathematical statements. Okay, just give me 1 second. I'm gonna go get a glass of milk. I love milk. I'm gonna go get a glass of milk and come back. Okay. Here's a crucial insight. He constructed a special statement G that when decoded basically says statement G cannot be proven in the system. Now let's see why this creates a paradox. Suppose G is provable in our system, then G would be true. But G itself says it can't be proven. Contradiction. Suppose G is provable in our system, then G would be true. But G itself says it can't be proven. Contradiction. Suppose G is disprovable. So this is the first case as earlier that we talked about. We can just take this out. I think because if G is provable, then it's not G, because if it were G, then it wouldn't be provable because we define G as not provable, I think. Suppose G is disprovable. We can prove it's false. Okay, so and then we would have proved that G can actually can be proven. Um, okay, so yeah, so we take this out too, right? Because if it is disprovable, if we can prove it's false, then well, then it's not yeah, then it can't be proven in the system, but then we would have proved that G can be actually can be proven. Now we prove that G cannot be proven. Then we prove that G is disprovable. Okay, now I'm getting tired. Therefore, G must be a true statement that cannot be proven within the system. Therefore, G must be a true statement that cannot be proven within the system. Therefore, G must be a true statement that cannot be proven within the system. Statement G cannot be proven in the system. If G is provable, then G would be true, but G itself says it can't be proven. So we can take that out. So we don't even need to assume that G is provable since we already said that G is not provable in the system, right? Am I right about this? This actually, this point, the first case here that we talked about earlier too, talked about case one, somewhere here. can find it. Yeah. Okay, here. So I think this statement and this statement are the same, right? But this statement is not in Claude's answer. Is this negative? Does this mean negative? Is that what this is? What does that mean? Okay, it's a negation, so it's like bar, so it's negative. Okay. Okay, so if G is not provable, um, then the probability predicate G is not provable, which is fine. It holds because that's how we define by definition of G. This means G is true. That does mean G is true, but does G exist? That's where I'm stuck. How do we know G is in the system? That's where I'm stuck right now. I'm not even I don't even start talking about what I started the stream for, but this is actually very fun so far. Okay, therefore G must be a true statement that cannot be proven within the system. So I guess I'm gonna spend the next 30 minutes of the stream trying to understand the incompleteness theorem uh, before moving on to other stuff. Okay. Um, yeah, it's similar to the liar paradox. This sentence is false, but Gödel, uh, it's also called like the equanimity paradox, I think. It has another name. I just need to remember the name. Uh, equanimity paradox, is that what it's called? Uh, equanimity. Okay. Okay, Epimenides. Okay, Epimenides paradox, right? Okay. Uh, this sentence is false, but Gödel found a way to express this idea purely in mathematics, and it is an idea that can exist within mathematics. Okay, amazing. Just as the liar paradox can be resolved as either true or false, G cannot be proven or disproven within a system. The okay, profound indicates that in any consistent mathematical system, complex enough to include basic arithmetic, there will always be true statements that okay, so how do we know G is true in the system? Um let me explain simply. Let me explain why we know G is true. Even though we can't prove it within the system. The key is understanding exactly what G says. G doesn't directly say I cannot be proven. Rather, through Gödel's encode, it says something more precise. There does not exist a proof of me in the system. Ah, okay. But how do we know G is in the system or that G is true in the system even if it does? I don't care. Thing is, I don't mind that G does not have a proof in the system. I don't mind that. That's totally fine. But I want to understand how do we know that? Okay, uh, now here's why we know G is true. I guess Claude is gonna answer now. We can prove from outside the system that if G were false, okay, so we're going outside the system now, which is kind of forbidden territory. That if G were false, it would lead to a contradiction. If G was false, it would lead to a contradiction. Well, yes, because we're assuming G is true, but we're assuming G is true, isn't that the case? This would mean there does exist a proof of G in the system. Okay. So let's continue. But we already showed this is impossible, that it would create a contradiction. Yeah, therefore G cannot be false. If G, okay, but how do we know G is in the system? Imagine someone says, okay, since G cannot be false, it must be true. This is a proof by contradiction. But notice we did this reasoning from outside the system. Okay, so I think the key here is that we're doing reasoning from outside the system. Let's see. Let me turn on the light and see. Okay, so there does not exist. So G says there does not exist a proof of me in the system. Okay, if G were false, that would mean a statement there does not exist a proof of me is false. Okay, so G says there is not a proof of me in the system. If G was false, then that would mean that there is a proof of it in the system, which would be a contradiction because it would be contradict itself. It has to be true, right? Because if it were false, then that would mean that there is a proof of it in the system. But uh, but we already showed this is impossible because it created a contradiction. Yeah, because it says G says there is not a proof of me in the system. If it was false, then that would mean there is a proof of it on the system, and if there is proof of it, then it is true, and that would mean it's false and true at the same time, which doesn't make sense. I don't mind that, okay? But I don't understand why we're assuming G in the system. Okay, my internet keeps disconnecting for whatever reason. Um, okay, so you assign numbers. Okay, so then you show that you can write formulas that talk about these numbers. Okay, so you can write a formula that checks if number X encodes a valid proof of the formula encoded by number Y. Okay, here's the magic. Okay, through some very clever mathematical work. Interesting. We'll have to look into that at a later stream. Not today because today's stream is kind of long already. It's not long yet, but with the stuff that I want to talk about, it's gonna. I don't think we have time. Actually, maybe that's what we should do. I don't know. We'll see. Through some very clever mathematical work, he showed how to construct a formula G that, when you decode what it's saying about numbers, means there does. Oh, So you construct the formula G. So you so he explicitly was able to construct G within S. Yes. Okay. Uh, okay. First, he created what we call the probability predicate. Probability y in the system's language. This formula takes a number y and returns true if y is the Gödel number of a provable formula. Okay, so it is a Boolean function as we were talking about earlier. So it is indeed a Boolean function. Okay, amazing, amazing. Then he used what's called the diagonalization lemma, a key technical tool. This lemma shows that for any formula f of x, you can construct a sentence S that is equivalent to Fs, where S, so like S brackets is the Gödel number of S. Okay. So you can construct a sentence S that is equivalent to Fs brackets, where S bracket is the Gödel number of S. If for any formula f of x, you can construct a sentence S that is equivalent to F bracket S, where bracket S is the Gödel number of S. Oh, so okay, so you can make oh okay, so you can make any, so there is a way to make for um any formula, okay, any formula f of x, you can put any sentence s in it to receive, you can put a sentence s in it to receive the Gödel number of s. For example, let's say f of x equals x. Um, you can put, there's an s, there's a sentence s, let's say f of 1, that you can put, which will give you the Gödel number of s. I guess you also have to think about how you arrange the Gödel numbers, how you define the Gödel numbers, but okay, interesting. I have to go, I have to look into it. So I guess this is a key technical tool, as we said, as Claude said. Applying this to f of x, not provable x, we get the formula g that is equivalent to not provable. So f of x equals not probability x, we get the formula g that is equivalent to not probability g. Okay, So let's say the formula is not probability x. We get the formula g that is equivalent to not probability g bracket. Okay. Okay. No, no. So this means let's assume like f of x is equal to x. You can construct a sentence as, for example, the number one, which is equal to f of x, and in x you put the Gödel number. We get so not probability x. We get the formula g that is equivalent to not probability Gödel number g. So G literally says the Gödel number of this formula is not provable. Hmm. So it's using the Gödel number as the as a thing it refers to that is not provable. So what it's saying, so what it is, oh, okay. I think I get it. Okay. So let me try to let's try online sketch. So as far as I understand, um, let's see. So as far as I understand, we have like symbols here like plus, minus, uh, times, etc. Right? Okay. Here we have numbers 1, 2, 3, 4, etc. Now we connect 1 to 1, etc. Right? We connect these 1 to 1. Okay. So here's the thing. Here, what we do is we say um, so we have G here and we have G bracket here, right? So by the way, I'm taking my time in this live stream, but later I'm gonna make this into a video, so to be shorter. Um, okay, let's come back here. Okay, so G says, this is what G says. G not provable. This is what G says. What this says, this is just the number n that this statement maps to, right? Okay. The actual formula G would be very long and complex when written out fully in arithmetic, but can be explicitly constructed following these steps. Think of it like writing a computer program. prints its own source code. It seems impossible at first, but there are clever ways to do it. Gödel found a similar trick in mathematical logic. Think of it like writing a computer program that prints its own source code. What's amazing is that before Gödel, as far as we know, no one thought you could make a mathematical formula that talks about itself in this way. Interesting. It's kind of like programming. I have to look into it. I have to add this, study this more. Would you like me to explain more about how the encoding system works? Okay, so I guess the next question I want to ask is, um, uh, so so Gödel's the Gödel number. Actually, let me just copy this symbol right here. So G says this can't be proven, and if G and if this is mathematically shown to not okay can be proven indeed when then G is true and can't be proven. Yes, exactly. You've hit on the key point. Let me make sure I'm following your understanding. G is constructed to be equivalent to bracket G cannot be proven in the system. Okay. Where bracket G is just the Gödel number that includes G. Okay, so here's the thing. The system can be explained in terms of A right here or B right here. A and B, they both refer to the same system. One refers to it with symbols, the other refers to it with numbers. So G is saying that the other form of the system, the G in the other form of the system, is not provable. If G says that G in the other form of the system is not provable, then that means that G in the other form of the system says the same thing. It says G in the other form of the system is not provable. So G says the G's form in B is not provable, which means G as in its B form says that G in the A form is not provable. Okay, so we can understand the reciprocity, right? Okay, so I get the reciprocity. And then we reason. If G could be proven, then G bracket would be provable. But G says G bracket is not provable. So G says, okay, so G says G bracket, so G says G bracket is not provable. I'm gonna have to watch a video about this after I read this. But G says G bracket is not provable. So if G were provable, it would be false. Contradiction. If G were provable, it would be false. Contradiction, yes, because it's not supposed to be provable. Therefore, G cannot be proven. And since G cannot be proven, what G claims that G bar cannot be proven is actually true. Okay. Okay, I get it, I think. I think I get it now. I don't just think, I'm pretty sure I get it. Okay, so the conceptual idea is that we have a system. We uh, form the system in another way. And then we say G is not provable in its form in the other system. Once we say that, that means either this G in A, right? Either that G or the G in B, regardless from which one you start, it doesn't matter. It doesn't even matter how you represent the other system, I think. I'm not sure about it. What that means is that G in whatever form in any system, or in whatever form in the system, in whatever form of the system, cannot be proven in the other form of the system. Once we say that, and once G itself says that it is not provable in the other form of the system, let me read this again. The thing is, I just got it, but I need to hold it down in my mind. So if G were provable, it would be false, contradiction. Therefore, G cannot be proven. And since so if G were provable, it would be a contradiction. Ah, so remember the case one from earlier that I said is just to clear up the clutter. Apparently, it's a very important case that we should take into consideration. Not only we should take into consideration, it's important in the proof of the theorem. So if G were provable, it would be false. So if G were provable, then G bracket or G in the other form would be provable as well. And and we cannot allow that because what we said is we, we said that G in the other form is not provable. Okay? So we cannot allow that because G in the other form is not provable as G is defined. And we can represent G in the other form. So G in the other form is not provable. If G were provable, then G in the other form would be provable, at which moment G would be false and it would be a contradiction. It would be a contradiction because it will be not provable, but also provable. Because it says it's not provable, but somehow it's provable, so it should be not provable. Therefore, G cannot be proven. And since G cannot be proven, what G claims that G bracket cannot be proven is actually true. And since G cannot be proven, as we just proved that it cannot be proven, then that means, by its definition, G is just true because we just proved it's true because we just proved it's not provable. Okay, I think I get it. I think I get it. Okay. Let's uh let's go through this again. Okay, so this is a very important mapping, I think, to understand why G is not provable. Okay, so let's go through this again. And by the way, I think Claude did a better job than DeepSeek. DeepSeek just kind of talks too much. Really. But anyways, that's not a problem. Okay, DeepSeek, Claude doesn't talk that much. And so. Um, so what G says, G actually like does not immediately say. When we define G, G does not immediately say that it is not provable. What it says is that G in its other form of the system is not provable. And if G in the other form of the system were provable, then G would be provable. Then it would be false. G here would be false. But we just said it's provable, then it would be provable and not provable at the same time, and that would be a contradiction. So it's not provable and not provable at the same time, which means the only other option is that it's not provable. And if G is not provable, then G bracket is not provable. And if G bracket is not provable, then that means G is true because we just proved that G bracket is not provable and G is defined as G is not provable. So that means G is indeed in the system. G is indeed in the system. Why? Because its definition is true. We can prove the definition is true because G bracket we just proved is not provable because it being not provable is the only option, because the only other option is it being provable, and it being provable is impossible, because if it were provable then it would have to be provable and not provable at the same time. Because if it were provable, then that implies it's true. It's true in the system. It's true and provable in the system. So it's true. It's provable that it's not provable. So it's true. What is true is that it's provable and provable at the same time as it can be. Anyways, I think okay. So I understand now. Beautiful. Beautiful. Okay, I get it. Amazing. Lovely. Oh, that took some time to understand, bro. Okay, let's go. Let's watch a YouTube video about Gödel's theorem just to calm our minds a little bit, to understand a little bit better, to apply what we just learned. Uh, and then um, and then we'll move on to the other subject that I was going to talk about. But now that we went this far into why Gödel's incompleteness theorem is actually true, I think I would rather see some formalism. Actually, oh no, what's this? Um, oh, my camera looks kind of bad. Let me. And then we'll move on to the other subject that I was going to talk about. But now that we went this far into why Gödel's incompleteness theorem is actually true, I think I would rather see some formalism. I can't hear myself in the laptop. Oh, wow. Wow, I'm very laggy though. Um, no, my camera looks kind of bad. Let me. And then we'll move on to the other subject that I was going to talk about. But now that we went this far into why Gödel's incompleteness theorem is actually true, I think I would rather see some formalism. Okay, I can't hear myself. Let me check the stream on my phone. But now that we went this far into why Gödel's incompleteness theorem is actually true, I think I would rather see some formalism. Okay, I can't hear myself. Let me check the stream on my phone. So, uh, so what G says, G actually like does not immediately say. When you define G, G does not immediately say that it is not provable. What it says is that G in its other form of the system is not provable. And if G in the other form of the system were provable, then G would be provable. Then it would be false. G here would be false. But we just said it's provable, then that would be then provable and not provable at the same time, and that would be a contradiction. So it's not provable and not provable at the same time. Which means the only other option is that it's not provable. And if G is not provable, then G bracket is not provable. And if G bracket is not provable, then that means G is true because we just proved that G bracket is not provable and G is defined as G is not provable. So that means G is indeed in the system. G is indeed in the system. Why? Because its definition is true. You can prove the definition is true because G bracket we just proved is not provable because it being not provable is the only option. Because the only other option is it being provable, and it being provable is impossible. Because if it were provable, then it would have to be provable and not provable at the same time. Because if it were provable, then that implies it's true and the system it's true and provable. It's true, it's provable that it's not provable. But it's true. What is true is that it's provable and unprovable at the same time as I can be. Anyways, I think, okay, so I understand now. Beautiful. Beautiful. Okay, I get it. Amazing. Oh, that took some time to understand, bro. Okay, let's go, let's watch a YouTube video about Gödel theorem just to calm our minds a little bit, to understand a little bit better, to apply to what we just done. Okay, amazing. Okay, the video is kind of laggy. I'll have to find a way to fix that. Maybe I'll see how I'm gonna do that in the next stream. Let me check something really quickly. Wow, that's kind of mind blowing. Okay, so what do we do now? Let's watch a video on Gödel's incompleteness theorem just to understand it better for like 10 minutes, 15 minutes, and then let's read some formalism about his theory. Probably let's read his original paper. Okay, so Gödel's incompleteness theorem. I don't feel like it's a paradox though. I mean, I'm a firm believer that there are no paradoxes, actually, so I'm kind of biased. but I don't think it's a paradox. I, I feel like it's not a paradox. We start with this dead.
Consider the following sentence. This statement...
I can't hear anything. Um, that is an issue. I want to be able to hear the video.
is false.
I
Is that
think the
true? If
tab
so,
is
that would make
going on the screen, so I can
this statement false. But if it's false, then the statement is true.
Yeah,
By referring to
this
itself directly,
audio
this
as well,
statement
but
creates
I
an
cannot
unresolvable
actually
paradox. So if it's not true and it's not, this question might seem like a silly thought experiment, but in the early 20th century, it led Austrian logician Kurt Gödel to a discovery that would change mathematics forever.
Maybe it's because I'm wearing headphones.
Undeniable statements about the numbers involved. Every system built on
I
mathematics.
guess I have to take off my headphones. Is it? Okay, let me take off my. Okay, I can hear now. Let me check.
Consider the following sentence. This statement is false. Is that true? If so, that would make this statement false.
Well, okay, but here's the thing. Here's the thing. It doesn't say this statement is false. It says this statement is unprovable. Unprovable. And we can prove it's true. We can prove it's true. But if we prove it's true, then it's false. Then it's unprovable. But unprovable but true because it's unprovable but true because the other statement, because it needs like a duality with the number system. Well, it does. I think the thing is, what resolves it from being a paradox is that it implicitly requires a contrast with another form of the system. Technically, if a system cannot have another form, technically, let's assume there's a system that cannot have another form in any way, shape, or form, then it's not a paradox there, because it's simply it's a false statement. Why? Because there's no other form of the system that can be contrasted against. I think we have to look into it. Okay, so let's see.
Consider the following sentence. This statement is false. Is that true? If so, that would make this statement false. But if it's false, then the statement is true. By referring to itself directly, this statement creates an unresolvable paradox. So if it's not true and it's not false, what is it? This question...
Okay, so without headphones, my voice doesn't have isn't as good. Actually, I'll have to fix the sound issue next time too. But let's continue watching this video as it is for now.
Consider the following. Consider the following sentence. This statement is false. Is that true? If so, that would make this statement false. But if it's false, then the statement is true. By referring to itself directly, this statement creates an unresolvable paradox. So if it's not true and it's not false, what is it? This question might seem like a silly thought experiment, but in the early 20th century, it led Austrian logician Kurt Gödel to a discovery that would change mathematics forever. Gödel's discovery had to do with the limitations of mathematical proofs. A proof is a logical argument that demonstrates why a statement about numbers is true. The building blocks of these arguments are called axioms, undeniable statements about the numbers involved. Every system built on mathematics, from the most complex proof to basic arithmetic, is constructed from axioms. And if a statement about numbers is true, mathematicians should be able to confirm it with an axiomatic proof. Since ancient Greece, mathematicians used this system to prove or disprove mathematical claims with total certainty. But when Gödel entered the field, some newly uncovered logical paradoxes were threatening that certainty. Prominent mathematicians were eager to prove that mathematics had no contradictions. Gödel himself wasn't so sure, and he was even less confident that mathematics was the right tool to investigate this problem. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. A mathematical statement is simply true or false, but Gödel had an idea. First, he translated mathematical statements and equations into code numbers, so that a complex mathematical idea could be expressed in a single number. This meant that mathematical statements written with those numbers were also expressing something about the encoded statements of mathematics. In this way, the coding allowed mathematics to talk about itself.
Okay, so let's pause right here for a second. Actually, let me put my headphones for a good sound. Okay, so here's the thing. If you cannot do this, if you cannot represent the formulas in numbers, then the proof doesn't work. And I think that's what saves it from being a paradox. Because if we assume, or if we, uh, or if we uh, think about a system that cannot be presented in numbers, then there is no paradox. Because that's what the proof builds upon. I'm not saying the proof is wrong. I think the proof is 100% right. It only encompasses systems, or like those are most systems that we deal with, but it only encompasses systems that can be represented as numbers.
Into code numbers, so that a complex mathematical idea could be expressed in a single number. This meant that mathematical statements written with those numbers were also expressing something about the encoded statements of mathematics. In this way, the coding allowed mathematics to talk about itself. Through this method, he was able to write "this statement cannot be proved" as an equation, creating the first self-referential mathematical statement. However, unlike the ambiguous sentence that inspired him, mathematical statements must be true or false. So, which is it? If it's false, that means the statement does have a proof. But if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement can't be false, and therefore, it must be true that this statement cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statements still are either true or false, but true statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove. Even if you account for these unprovable statements by adding them as new axioms to an enlarged mathematical system, that very process introduces new, unprovably true statements. No matter how many axioms you add, there will always be unprovably true statements in your system. It's Gödel's all the way down. This revelation rocked the foundations of the field. Even if you account for these unprovable statements by adding or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove, even if you because they're false. So, which is it? If it's false, that means the statement does have a proof. But if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement can't be false, and therefore it must be true that this statement cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statements result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot. That means the statement does have a proof, but if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement can't be false, and therefore it must be true that this statement cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statement of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which yet this result is even more surprising. Statement can't be false, and therefore it must be true that this statement cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statements still are either true or false, but true statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unproven but true statements can either be provable or at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statements still are either true or false, but true statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. The given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using
Okay, so just one thing here. I have to look into whether um, so he said in every system that in every mathematical system or in every system there must be true statements that can't be proven. Alright, in
unprovably
every
true
axiomatic system.
statements exist
Uh,
be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every
exist in every axiomatic system. Well, so the question is there any axiomatic system that cannot be mapped into another form of system like numbers? That is the question that I need to know the answer to. Because I don't know. It feels like there may be. That's something that I'm gonna research more and to understand. Um, or maybe that isn't considered an axiomatic system, but it feels to me there can be axiomatic systems like that, or one axiomatic system like that. I'll be looking into that.
or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove. Even if you account for these unprovable statements by adding them as new axioms to an enlarged mathematical system, that very process introduces new, unprovably true statements. No matter how many axioms you add, there will always be unprovably true statements in your system. It's Gödel's all the way down. Unprovably true statements in your system. It's Gödel's all the way down. This revelation rocked the foundations of the field, crushing those who dreamed that every mathematical claim would one day be proven or disproven. While most mathematicians accepted this new reality, some fervently debated it. Others still tried to ignore the newly uncovered hole in the heart of their field. But as more classical problems were proven to be unprovably true, some began as more classical this new reality, some fervently debated it. Others still tried to ignore the newly uncovered hole in the heart of their field. But as more classical problems were proven to be unprovably true, some began to worry their life's work would be impossible to complete. Still, Gödel's theorem opened as many doors as it closed. Knowledge of unprovably true statements inspired key innovations as would be impossible to complete. Still, Gödel's theorem opened as many doors as it closed. Knowledge of unprovably true statements inspired key innovations in early computers. And today, some mathematicians dedicate their careers to identifying provably unprovable statements. Dedicate their careers to identify early computers. And today, some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for certainty. Unprovable statements. So while mathematicians may have lost some certainty, thanks to provable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. Statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. Unprovable statements. So while mathematicians may have lost some certainty, thanks and today some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost in early computers, and today some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians innovations in early computers, and today some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart. May have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. And today, some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. Unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. The Pythagorean theorem has more than 300 provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. The Pythagorean theorem has more to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. The Pythagorean theorem has more than
Okay. Another thing I want to point out here. Let's come back here. So, um, another question with Gödel's incompleteness theorem is: are all axioms unprovable, or are all axioms true but unprovable? And I don't think so. I simply don't. Here,
in them
the
as
thing is,
new
when they
axioms
said
to
here
an
that
enlarged
they goes
mathematical
all the way
system.
down,
That very
feels like
process
the basis
introduces
of
new
mathematics is unprovable, and that I don't believe that is the case. But that isn't what they mean. I don't think that's what they mean here. What they mean is that there's unprovable true statements everywhere in all systems. Okay. Um, So I will come back to this in around 15 minutes. I've been really enjoying this stream. I'm gonna put a timer. I'm gonna go take a rest for 15 minutes and come back. Um, I just learned how to prove Gödel's incompleteness theorem, which is awesome. I'm gonna come back. When I come back, let's read his paper. I think if we have time, hopefully I have time. Um, 5 minute interval timer. Okay, I'm gonna put this at 15 minutes. Okay, so 15 minutes. I will be back in 15 minutes. I'm just gonna take a break. It's amazing stream, by the way. This is my third stream ever. Awesome stream. Lovely. Learned a lot of stuff. It's going awesome. I'm gonna do this, hopefully. I'm gonna do this every day. God willing. Okay? So I'm gonna go for 15 minutes and come back. We're gonna continue reading Gödel's incompleteness theorem in his own paper this time. See you in 15 minutes. Hello, 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 hello. I'm back. I am back. I took like 30 minutes. So, hey, yeah, I took kind of long. Anyways, I'm back. Um, replenished my milk. Let's see what time is it? 7:15. We probably have like 30 minutes to read Gödel's incompleteness theorem at pistachio as well. Okay, let's get to work. So, okay, so I think I'll just put it over here. Okay, let's just go to ChatGPT now. Um, maybe I have already downloaded the paper. Let me see. Actually, let me just look for it. The link of all the PDF of the incompleteness theorem paper. Sure. Okay. Okay, 79 pages. Beautiful, amazing. Okay, Kurt Gödel on formally undecidable propositions of Principia Mathematica and related systems. Okay, so he's basing his um, a theory on Principia Mathematica type of systems, like related systems. So it probably encompasses all of them, standard mathematics. To Christopher Fernald, in fact. Preface. Okay, let's read the preface. We're gonna read this over multiple live streams. Preface. Kurt Gödel's astonishing discovery and proof, published in 1931, that even in elementary parts of arithmetic there exist propositions which cannot be proved or disproved within the system, is one of the most important contributions to logic since Aristotle. Yes, I mean, yeah, it is a very important one. Any formal logical, by the way, let me check if the sound works. Okay. Any formal logical, by the way, let me check if the sound works. Okay, I think I have to use different earbuds this time too. Anyways, let's continue. Any formal logical system which disposes of sufficient means to compass the addition and multiplication. Any formal logical system which disposes. What do you mean disposes? What does disposes mean? Doesn't disposes mean that it doesn't mean get rid of? Okay, any formal logical system which disposes of sufficient means to compass the addition and multiplication of positive integers and here is subject to this limitation. So that one must consider this kind of incomplete and inherent characteristic of formal mathematics as a whole. Okay, I guess I'm gonna ask. AI at some point experimenting with this position here, but this isn't in the actual paper, so we can proceed it for now. So that one must consider this kind of incompleteness an inherent characteristic of formal mathematics as a whole. By the way, how does my hair look? Okay. So that one must consider this kind of incompleteness as an inherent characteristic of formal mathematics, an inherent characteristic of formal mathematics as a whole, which was before this customarily considered the unequivocal intellectual discipline par excellence, which was before this customarily considered the unequivocal intellectual discipline par excellence. It still is the unequivocal intellectual discipline par excellence. Wherever there are holes in mathematics, those holes apply to everything else as well. So it's still the unequivocal intellectual discipline par excellence, because its limitations with all other subject matter limitations as well. Non-English translation of Gödel's paper, which occupied 25 pages of the Monatschrift für Mathematik und Physik, has been generally available, and even the original German text is not everywhere easily accessible. The argument, which uses a notation adapted from that of Whitehead and Russell's Principia Mathematica, is a closely reasoned one and the present translation, besides being a long overdue act of piety, should make it more easily intelligible and much more widely read. In the former respect, the reader will be greatly aided by the introduction contributed by the knight professor of moral philosophy in the University of Cambridge, for this is an excellent work of scholarship in its own right, not only pointing out the significance of Gödel's work, but eliminating it by paraphrase of the major part of the whole great argument, not only pointing out the significance of Gödel's work, not only pointing out the significance of Gödel's work, but eliminating it by paraphrase of the major part of the whole great argument, not only pointing out the significance of Gödel's work, not only pointing out the significance of Gödel's work, but eliminating it by paraphrase of the major part of the whole great argument. Okay, interesting. I propose publishing a translation after a discussion meeting on Gödel's theorem and its bearing on the philosophy of science, held in 1959 by the Edinburgh Philosophy of Science Group. I wish to thank this society for providing the stimulus, the publishers for their ready cooperation on the proposal, and Professor Braithwaite not only for the introduction but also for meticulous assistance in translation and proofreading of a critically intricate text. It may be noted here that the pagination of the original article is shown in the margins of the translation, while the footnotes retain their original number. B. Malta, University of Edinburgh, January 1962. It's been 63 years. Yeah, 63 years. Okay. Introduction by R.D. Berthelot. Paraphrase. Every system of arithmetic contains arithmetical propositions, by which is meant propositions concerned solely with the relations between whole numbers, which can neither be proved nor disproved within the system. Every system of arithmetic contains arithmetical propositions by which is meant propositions concerned with the relations between whole numbers, which can neither be proved nor be disproved within the system. This epoch-making discovery by First Gödel, a young Austrian mathematician, was announced by him to the Vienna Academy of Sciences in 1930 and was published in 1930. That's 95 years ago, and was published with a detailed proof in a paper in the Monatschrift für Mathematik und Physik, volume 38, pages 173 to 198. This paper, entitled Über formal unentscheidbare Sätze der Principia Mathematica und verwandter Systeme I, or 1, on formally undecidable propositions of Principia Mathematica and related systems 1, is translated in this book. Gödel intended to write the second part of the paper, but this has never been published. Interesting. We'll have to look into later if he ever wrote a second part anywhere else, or what we can figure out about the second part. Gödel's theorem, as a simple corollary of proposition 6, page 57, is frequently called proves that there are arithmetical propositions which are undecidable. I'm getting tired, bro. Okay. Proves that there are arithmetical propositions which are undecidable, i.e., neither provable nor disprovable within their arithmetical system. And the proof proceeds by actually specifying such a proposition, namely the proposition G, expressed by the formula to which 17 Gen R refers, page 58. G is an arithmetical proposition, but the proposition that G is undecidable within the system is not an arithmetical proposition, since it is concerned with provability within an arithmetical system, and this is a meta-arithmetical and not an arithmetical notion. Yes, it's more, you could say, it's the notion, it's a logical notion, or it's a logical notion that encompasses arithmetic. So it's like a broader field. Gödel's theorem is thus a result which belongs not to mathematics, but to metamathematics. Well, I think it does. It belongs to mathematics. It belongs to the field of logic, and it just depends on whether or not you want to consider logic mathematics. And it's just a question of terms. But to metamathematics, the name given by Hilbert to the study of rigorous proof in mathematics and symbolic logic. But The name given by Hilbert to the study of rigorous proof in mathematics and symbolic logic. Meta-mathematics, Gödel's paper presupposes some knowledge of the state of meta-mathematics in 1930, which therefore I shall briefly explain. Following on the work of Gödel and Peano, Whitehead and Russell's Principia Mathematica had exhibited the fundamental parts of mathematics, including arithmetic as a deductive system. Starting from a limited number of axioms, in which each theorem is shown to follow logically from the axioms and theorems which precede it, according to a limited number of rules of inference. And other mathematicians had constructed other deductive systems, which included arithmetic. In order to show that in a deductive system every theorem follows from the axioms according to the rules of inference, it is necessary to consider the formulae which are used to express the axioms. It is necessary to consider the formulae which are used to express the axioms and theorems of the system. Yes. And to represent the rules of inference by rules, Gödel calls them mechanical rules. We could call them that, but I think they can be reduced to concrete mathematical rules. In my opinion, they can be reduced to logical rules. Okay, whether you want to call them mechanical, sure, but they can be reduced to concrete logical rules in my opinion. I'm gonna have to read about, I think, um, category theory maybe? Category theory, maybe combinatorics, I'm not sure. According to which, from what? According to which, from one or more formulae, another formula may be obtained by manipulation of symbols. According to which, from one or more formulae, another formula may be obtained by a manipulation of symbols. Yes. Such a representation of a deductive system will consist of a sequence of formulae, a calculus, in which the initial formula expresses the axioms of the deductive system and each of the other formulae, which express the theorems, are obtained from the initial formulae by a chain of symbolic manipulations. The chain of symbolic manipulations in the calculus corresponds to and represents the chain of deductions in the deductive system. The chain of symbolic manipulations in the calculus corresponds to and represents the chain of deductions. Let me read this again. The chain of symbolic manipulations in the calculus corresponds to and represents the chain of deductions in the deductive system. Okay, but this, as far as I think what he's saying, like there is a chain of deductions that is like the framework, and the chain of symbolic manipulations is corresponding to that framework. So you have like a function, uh, like programming function, for a chain of deduction that determines how the symbolic manipulations can be carried out. But this correspondence between calculus and deductive system may be viewed in reverse. And by looking at it the other way around, Hilbert originated metamathematics. But this correspondence between calculus and deductive system may be viewed in reverse, and by looking at it the other way around, Hilbert originated metamathematics. The this correspondence between calculus and deductive system may be viewed in reverse, and by looking at it the other way around, Hilbert originated mathematics. I mean, sure, of course, you can look at it in reverse, of course. Uh, I mean, yeah, basically, I mean, okay, I need to understand what they mean by reverse exactly, but again, I mean, if f of x equals x, so x equals f of x, and that's what that means. Here, a calculus is constructed independently of any interpretation of it, as a sequence of formulae which starts with a few initial formulae. Here, a calculus is constructed independently of any interpretation of it. Oh, yeah. As a sequence of formulae which starts with a few initial formulae, and in which every other formula is obtained from the second formulae by symbolic manipulation. Ah, okay. Of course, yeah. Yeah, I mean, you don't need to define what kind of formula you can get from the original axiom. You can make any original formula, and whatever formula those formulae imply, then you just include that in your system, in your calculus, in your system. The calculus can then be interpreted as representing a deductive system. If the initial formula can be interpreted as expressing the axioms of the system, and if the rule, let me read this again. The calculus can then be interpreted as representing a deductive system. The calculus can then be interpreted as representing a deductive system. Talking out loud for a long time kind of makes my head makes me lightheaded. The calculus can then be interpreted as representing a deductive system. If the initial formulae can be interpreted as expressing the axioms of the system, the calculus can then be interpreted as representing a deductive system. If the initial formulae can be interpreted as expressing the axioms of the system, and if the rules of symbolic manipulations can be interpreted as representing the logical rules of inference of the system. I agree. Yes. I don't. Yes. Yes. I don't need to wait for any. If this can be done, it proves that a formula other than one of the initial formulae. If this can be done, it proves that a formula other than one of the initial formulae it proves that a formula other than one of the initial formulae occurs in the sequence of formulae of the calculus yields the proof that the proposition, which is the interpretation of this formula, is a theorem of the deductive system, i.e. can be deduced from the axioms of the system by the system's rules of inference. Basically, what this is saying is you can make initial rules, and whatever extra whatever other rules these rules imply or like you can infer from these rules, they all are in your system. Meta-mathematicians in the 1920s, so I guess the difference between meta-mathematics and mathematics, is that in meta-mathematics, you allow for all consequences um, from the initial actions. In mathematics, you may not allow all consequences, not necessarily, unless you want to. I would say meta-mathematics here seems like a branch of mathematics. Meta-mathematicians in the 1920s established many important results about deductive systems. By converting proofs of what formulae by converting proofs of what formulae can be obtained by symbolic manipulations. Meta-mathematicians in the 1920s established many important results about deductive systems. Yes. By converting so yeah, by converting proofs of what formulae can be obtained by symbolic manipulations within a calculus and proofs of what theorems can be proved within a deductive system which could be represented by the calculus. Okay, so I need to read that again. Mathematicians in the 1920s established many important results about deductive systems by converting proofs of what formulae can be obtained by symbolic manipulations within a calculus and proofs of what theorems can be proved within a deductive system which could be represented by the calculus. The calculus into proofs of what theorems can be proved within a deductive system which could be represented. Okay. I guess, it's not this like already a tool of mathematics? Maybe back then they consider that mathematics. I need to look into what is the difference exactly. Let me create a screenshot. Okay. Frequently, consideration of symbolic manipulations provided a decision procedure for which whole classes of theorems could actually be proved. Frequently, consideration of symbolic manipulations provided a decision procedure. Frequently, consideration of symbolic manipulations provided a decision procedure by which whole classes of theorems could actually be proved. Yes, this method of this method of proof opens whole classes of theorems that can prove whole classes of different theorems that can prove that perhaps wouldn't be able to be proven through other ways. Thus, Presburger in 1930 published a decision procedure applicable to every proposition of a manipulated system of arithmetic which uses the operation of addition but not that of multiplication. He proved every one of his propositions is decidable, i.e. either provable or disprovable within the system. Thus, Presburger in 1930 published a decision procedure applicable to every proposition of a manipulated system of arithmetic which uses the operation of addition but not that of multiplication. He proved that every one of his propositions is decidable, i.e. either provable or disprovable within this system. So, as far as I understand, what he's saying is that um, if you, what Presburger in 1930 proved is that if you take out multiplication from arithmetic, he proved that you still have the same system. Gödel's paper established the opposite of this for an arithmetical system which uses multiplication as well as addition. The theory of ordinary whole numbers. And this is the piece of mathematics which is oldest in the history of civilization and which is of such practical importance that we make all our children learn a great deal of it at an early age. Gödel was the first to prove any unprovability theorem for arithmetic. Gödel was the first to prove any unprovability theorem for arithmetic. Gödel was the first to prove any unprovability theorem for arithmetic. And his way of proof was subtler and deeper than the mathematical method previously employed. Either of these facts would have ranked this paper high in the development of metamathematics. But it was the fact that it was a proposition of whole number arithmetic I'm tired, bro. Ah, maybe I should do some gaming. Maybe I should do some gaming. Okay, let me finish reading. Let me finish reading this paragraph, and we'll continue reading this paper. Maybe next time. I'm gonna finish reading this paragraph, and maybe let's do some gaming, and then I'm gonna peace out. Okay. Either of these facts would have ranked this paper high in the development of metamathematics. Okay, so, mhm. But it was the fact that it was a proposition of whole number arithmetic, which he showed to be undecidable, that created such a scandal. So he basically made a much better proof than metamathematical method, or a proof that is more accepted than metamathematical methods. I need to see why metamathematics, whether is metamathematics considered mathematics? Let's see. Let's ask Claude. Metamathematics. So metamathematics studies mathematics itself. Okay. Is metamathematics considered is mathematics considered a branch of mathematics when did it officially become so? Interesting. So from 1950s to 1970s, it started to be accepted well. But it started way before that in the first 1900s, in the 1920s, 1920s. Statistics is more considered as a okay. Either of these facts would have ranked this paper high in the development of metamathematics. Either of these facts would have ranked this paper high in the development of metamathematics. But it was the fact that it was a proposition of whole number arithmetic, which is showed to be undecidable, that created such a scandal. Okay, so why are they calling it undecidable instead of unprovable? And go back to this website. Why are they saying undecidable instead of unprovable? So you cannot decide whether the statement is true or false. The theorem also connects to the world of concept of decidability and conceivability. The decision problem is decidable if there exists an effective method, algorithm, that can determine whether any given instance has a solution. The decision problem is decidable if there exists an effective method, algorithm, that can determine whether any given instance Decision problem is decidable if there exists an effective method, algorithm. A decision problem is decidable if there exists an effective method, algorithm to determine whether any given instance has a solution. Interesting. Okay, so I think this is the key. This is the key thing in the theory. We have to look into this when we come back to it next time. In Gödel's work, he showed that for any consistent form of system powerful enough to encode basic arithmetic, there will be statements that can neither be proved nor disproved within that system. They are truly undecidable in the system. This is stronger than just being proved. Okay, okay, but I thought they are unprovable and true. This is sad but fascinating point. You're actually touching on something very important. The Gödel sentence G is indeed both undecidable, can be proven or disproved within the system, and the truth when viewed from outside the system. So when viewed from outside the system, that's the key point we were thinking we were talking about earlier. This is one of the most mind-bending aspects of Gödel's work. Inside the system, G can't be proved nor disproved. It's undecidable. But when we reason about it from outside the system, we can see that G must be true. So we have to reason about it from outside the system by connecting it to other form to the other form of the same system, and that connection is the outside of the system that makes the first incompleteness theory true. Which reminds us of the other thing that I was talking about earlier is what if we cannot do that? What if we cannot contrast it with another form of the same system? There is a system that can't be contrasted with another form. Then what happens then? But anyway, that's another point. That's another thing. We will talk about that after we read the paper, as I want to understand the paper very well first. But when you read about from outside the system, you can see that G must be true. Because if you were false, it would be provable, and it's going to be unprovable. But if it were provable, it would be true. Since the system is sound, these contradictions mean G must be true. Because it cannot be false and true at the same time. So this contradiction means G must be true. The G must be true because it's not provable, it's unprovable, and it says it's unprovable, so it's true. Therefore, we are going to sense both undecidable within the system and true when viewed from outside. Okay, so viewing it from outside is necessary. Okay, so if there is a system that can be viewed from outside, there is another thing to look into. The term undecidable refers to a status within the formal system. It refers to something within the formal system, not from the outside. While its truth value can be determined through mathematical reasoning, outside the system. Would you like me to elaborate on how this connects to the formal construction of the Gödel sentence? Okay, this was amazing. Let's um let's play some games. What should we? Yeah, let's actually do Neil.com. I'm gonna go bring my mouse. Let me play some games. And then I'm gonna go lay down for rest or whatever. I'm tired. How long has this stream been going, by the way? Let me see how long this stream been going. What's happening here, by the way? Okay. Is my internet slow? Oh, my internet is slow. My internet is slow and laggy. Next time it's gonna be better. I hope. I think I know how to fix it. It's gonna be awesome. My camera isn't perfect. It's fine. Maybe I can use my phone as a camera. We see. I'll look into it. Anyways, let's continue. So let's come to YouTube for a second. Let's see. Let's look at my okay, let me go get my mouse. I hope this works. It's not happening. I hope this works. It's not happening. Hello? Hello? Is my voice better now? I think my voice is better now. Okay, is this gonna work? Come on, brother. Am I on the wrong website? Oh, I was on the wrong website. Okay. Um, okay, so what do we do? Which game do we do? Let's just start with this one. Draw the circle. One, two, three. Of course I can draw a perfect circle. Watch this. Best score. Best. Okay. Look at this. Okay. There we go. There we go. Well, when it's off-centered but still circular, it doesn't count it. Okay, amazing, amazing, amazing. Let's see what else. What is it? Internet artifacts. What is this? You may touch the artifacts. Okay, amazing. I like when museums say that. Ah, amazing, amazing. Okay, ARPANET, the precursor to the internet. 100 shown 111 computer connections of network in 1917. Wow. One in Hawaii, one in Utah. Wow. One in MIT. Oh my God. So like it was an internet over the whole country, ARPANET. Interesting, interesting. Mm. Stanford, NYU, NSA, Pentagon, Texas, Lincoln. I guess it's Lincoln, Illinois. I'm not sure. I don't know. Is there a city named Lincoln, Illinois? I'm not sure. Okay, space elevator. Okay, so fireworks, hummingbird, hot air balloon. Oh, how high is this? 17 meters. Let's see. Mallard, 1,000 meters. You got the Lario. First plane up to cross the English Channel. Interesting. Osprey, hang gliding, pigeon. So pigeons how high? Wow, pigeons 2 kilometers and a half. Bald eagle. Okay, so if we got some of it, it's like a level. What is this? The troposphere. So 99% water vapor is over here. These are nimbus clouds. Bald eagle, monarch butterfly. Okay, we're gonna play this another time more. Let's see what else we can play here. Oh, absurd trolley problem. Actually, let's do this. Wait. Okay, before we get to this. This is ambient chaos. I guess I need sound for this. I cannot hear. Because I'm wearing headphones and I need to fix it. Rocks, printing money. Yeah. The size of space, dark pattern. Okay, printing money, sell. Password game. Hmm. Paper, speed, lab triggers, 3D map, draw logos, spend Bill Gates money. Of course. Okay. You've got $100 billion. Okay, so let's buy 500 Big Macs. Kinda hungry. 20 flip-flops, 500 cola packs, 1,000, 10,000, I guess. Book. You want a large, right? Million. Is that a million? But I'm not even making a bank. A billion. Okay. Lobster dinner. No, wrong. Video game. Yeah, 70. Amazon Echo 2400. Year of Netflix 3500. No, no. No. One. We share the password here. No, 10. Okay. Uh, Air Jordans 3. No, no. 200. AirPods. You don't need AirPods. AirPods are overpriced. You can just get this. Or not this, isn't good ones, but there are good ones that are way cheaper than AirPods. Um, Gaming console 100. Drone 100. Smartphones 400. Bikes 1000. Acre of farmland, of course, of course. Okay. Anyways, draw logos from memory. Okay. Can oh, yeah, it doesn't have the dot really. Okay. Okay. Oh, really? Okay. Well, Starbucks is kind of complicated, but it's like this. I guess it has this thing. Yeah. Why did I reveal it? Okay. Pepsi, and this is blue. Oh, the blue is at the bottom. Okay. Twitter. Well, Twitter technically is this right now. Oh my god, I keep revealing it. Okay, okay, like that. NASA. Let's type this as well. Like that. No, need to do it like this. Okay. Android. Let's straight down. Spotify. Okay. What's this? Let's look at this. The internet, how do you pronounce GIF? GIF or GIF? Well, I don't know. Sometimes like this, sometimes like that, to be honest. Is the dress blue and black or white and gold? It's white and gold. It does have some blue though, I will say. Look, it is a little bit blue in the middle, but it's like it's light blue and gold. What? No, no, it's blue and gold. It's light blue and gold. Okay. What came first, the chicken or the egg? Um, the chicken, maybe? Should the sandwich be cut diagonally or horizontally? I'm not very sure. I need to think about this. Should the sandwich be cut diagonally or horizontally? Diagonally. Diagonally. The internet says cereal is not a soup. No, I agree. I agree. Cereal is not a soup. Toilet paper over or under? Over, over, over. If you do toilet paper under, you're a psychopath. That toilet paper is touching against the wall. Pepsi or Coke? Like Coke. 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 Is pineapple on pizza good? Never tried it. But I do want to try it. I do want to try it. Star Wars or Star Trek? I have no idea. I'm not sure. I guess Star Wars. I watched Star Wars, kinda. I don't quite remember it. Star Trek. I don't know. Is that even a movie? Is that a video game? I have no idea. I mean, yeah, let me see. Star Trek. I guess it's a movie. Yes, it's a media franchise. Oh, interesting. Oh, okay, that one. Oh, yeah. Star Wars better than Star Trek. Not. It's just Star Trek is like. Look at this. It's not. It's like explicitly lower quality. It's not. It's not like a big deal. Or is it? I have no idea. Anyway, I have no idea. I didn't really see it that much, but it seems like a lower quality. But it seems older too, which may give it like a legacy vintage priority, maybe. I don't know. I need to read. I need to watch it, I guess, to see. So I'm not sure if I'm gonna. I would see. I would see. A dog would wear pants like this. Yes, a dog would wear pants like that. Um, could Jack have fit on the door in the movie Titanic? Yeah, Jack could have, like, he could have walked through the door. Yeah, he could have walked through the door. Or is it supposed to block the door? It's supposed to block the door and like this, it's supposed to block the door too. Are hot dogs a sandwich? No, what do you mean? Hot dogs are a sandwich. Yes, hot dogs are a sandwich. There is no rule about sandwiches having to have two different buns. The two buns can be connected, brother. Yes, if a hot dog is a sandwich. Marvel or DC? I don't know. Should we get rid of daylight saving? No. No. Make daylight saving permanent. Dude, do you want shorter days? Do you want to wake up late? Do you want to lose all the sun time and make it all nighttime? Like, thing is, daylight saving would make it would make sunset 1 hour later. So sunset the day would be 1 hour longer. So it would be a longer day, more sun time. It's beautiful. At least I would prefer make daylight saving permanent. Abolish standard time. No, don't get rid of daylight saving. Make daylight saving permanent, please. Please, 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 please. Xbox or PlayStation? I don't know, but I think PlayStation. I'm not sure. Are we living in a simulation? Depends on what you mean. Depends on what you mean. But in general, yes, I think so. Is Die Hard a Christmas movie? I have no idea what Die Hard is. Middle brownie piece or edge piece? Middle, middle brownie piece. No, 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 middle. What do you mean edge? The middle one is has the chocolate. The middle piece is the juicy part. Not juicy, it's the chocolatey part. It's the nice part. It's like you're biting into molten chocolate, kind of. Middle part, 100%. Sock, shoe, or sock, shoe, shoe. Yeah, sock, shoe, shoe, I would say. iPhone or Android? No, oh, bro. You're just giving money to the world's largest corporation that doesn't even give you good products. It just gives, it just makes the product it just makes a new product every year. And the last year it was round, and this year it's circle square. That's it. There's no difference. They don't even make it any better. It's insane. They don't give you any privacy. They don't give you any rights. And you pretend, oh no, iPhone is better. Dude, iPhone is not better. Apple is brainwashing people into thinking iPhone is better. It's not. Android Android gives you control. Android gives you rights. Android respects you. iPhone doesn't even respect you. Anyways, Android for the W. Die hard. I mean, it's not that I'm pro Android, I'm against iPhone. Okay. Does it straw? I was already, by the way, the world's largest company, and they made all that money through freaking lying to everyone and making them buy stuff for no reason. Does the straw have one? Anyway, does the straw have one hole or two? Um, it depends on how you look at it, but it has two holes. Has the two holes at least. I mean, it has one hole and it also has two holes. It has both. Anyway, smooth or chunky peanut butter. Um, mm, I have both right now. I like it a little bit chunky. I don't like it too smooth. I don't like it too smooth. I like it to have a little bit of it. I don't like it. I mean, I don't mind it to be too chunky, but I'd like to have some bits, some texture. You know, I like it to be a little bit chunky. Well, I don't know if I were to choose between this or this one. I don't know which one I would choose, but I would like it. I like it a little bit chunky. Now that the internet has decided the big questions, we are finally free from the endless debates. Okay, okay. Now it's around 8:21 p.m. I'm gonna end the stream for now. It was a very nice stream, very beautiful stream, amazing stream. We learned a lot, we played a lot, we did a lot of stuff. We're gonna do more of these streams, God willing, and see you next time.